you pick a random dimension to split. Now you shouldn't actually pick one random dimension, you should pick, say, like 3 random dimensions and figure out which one works the best and take that. And if you just pick one, you're probably not going to be much better than the KD tree. You need to pick a few and pick whichever one works best. There's kind of this power of 2 choices phenomenon going on. But the one that's a little bit easier to work on is this kind of, let's call it the 2 means tree. Okay, so what we're going to do is instead of splitting based on some direction, you're going to let the data tell you how to split again. You're going to run a very simple clustering algorithm to cluster into 2 parts. You can do something like k-means clustering using Lloyd's algorithm for just a few iterations. And if you don't know what this is, we'll talk about it in like a week or 2. And you get 2 clusterings of the data. So you start with your data, like this, and typically there's some structure in the data. Okay, so you're going to pick 2 points, which are going to represent the centers of your clusters, and then this is actually, you're going to create the Voronoi diagram between these 2 points. And we'll see this is what this k-means clustering is doing. And this is your split. So I've still split with this line before, but I did it by clustering the 2 points into these 2 halves. So I said these are clusters. And they don't have to be great clusters. You don't have to run the algorithm, get the best answer. You just get some fairly decent answer. And then you repeat. So then I pick 2 more clusters. It can be the same point, that's fine. Say this point and this point. And now I split these 2 halves of the data. Okay, so I'm saying this is one cluster, and this is another cluster, and this is a cluster. But I'm using this midway line between the 2 points. And this you can do in any dimension. You can draw like a half space is defined in high dimensions by the line orthogonal to it. And the line orthogonal is the connecting line between the 2 points. So this is orthogonal in high dimensions. So this is now a splitting point. So it's also very easy to decide what side of these lines are on. And what's happening is this is automatically adapting to the structure of the data. Most data is not kind of uniform. There's some underlying structure. There's this manifold learning. People try and learn the structure. But often your data is kind of, there's something underlying there, and you automatically adapt to it. And you get these better and better fits as you do it. And you don't have to learn the structure. It automatically splits it for you. And this works, so this is basically what people use for the SIFT features nowadays. So when you get these 128 dimensional spaces, they tend to lie on some lower dimensional subspace. It's not a linear subspace, but it's some kind of curved subspace, and this will adapt to it, and you'll be able to find the points in roughly logarithmic time doing this. You still have to use this backtracking technique for the KD tree to find the stuff, but you now have a much better splitting plane that adapts to the data. And doing this clustering into 2 points is basically as easy as finding the median in one dimension.
And is it exact or approximate?
You can do exact or approximate. Again, doing approximate, it depends whether you're happy to satisfy with a slightly smaller block, or if you want to find the exact. Sometimes the exact will take a long time to run because of some funny situations, and the approximate is less likely to do that. So even setting epsilon to be like 0.001 will probably make a big difference. But it depends on the stopping conditions you have for your backtrack. So the same guy who actually invented the SIFT features has some code you can download to actually run this kind of this 2 means split tree. I forget what he calls it. And so I think you can download this code and use it. It's not the same production level as the ANN nearest neighbor structure, but it's supposed to work better, especially for the sort of data SIFT features are. For other sort of data, your mileage may vary. You may try one of these other techniques and it may work better. This is designed for Euclidean distance. It may not work as well for L1 distance or one of these other distances. Whereas the ball tree will work for any metric. So there are various things to try. Right. Great, so we'll start next week on